Okay, on the AP test, they love to give one or two multiple choice questions that are similar to this problem here, or the two problems that I've got here. So they say we've got some function y, which is equal to u times v. And then they say, I want to know what's the derivative of that function at some specific x value. And then they give you all this other information about u and about v and the derivative of u and the derivative of v, all at that same x value. So this is pretty straightforward. All they want to see is that you know what the product rule is and can do some basic arithmetic.
Wait,
So
shouldn't
go ahead.
Shouldn't the derivative be the same at any x value? Like, why is it at 2 specifically? Or
So the deal is we don't know what the function u is and we don't know what the function v is. They could be, I mean, they could literally be anything. But we know that u of 2 is equal to 3 and that u prime of 2 is equal to -4 and so on. And so we are looking for how does that affect this other function y and its derivative when we take the function y equal to u times v. And so no, it's specific to these actual values that are given to us.
okay.
Does that make sense or help or something?
Yeah.
Okay, cool. So if we're looking for the derivative of u times v, what rule should we use to find that?
Product rule.
Product rule. So y prime should just be u times v prime plus v times u prime. And if we want to find out what y prime at 2 is, then we just figure out what all of these are at 2 and evaluate. So u of 2 is 3. V prime of 2 is 2. V of 2 is 1. And u prime of 2 is -4. So this is just 6 minus 4 or 2. Easy enough? Yeah, no, maybe?
Yes.
All right. What if our function was u divided by v? What rule would we use?
Quotient rule.
We'd use the quotient rule. So that would be v times the derivative of u minus u times the derivative of v all over v squared. And we'll just plug in the values. V of 2 is still 1. And the derivative of u is still -4. U of 2 is still 3. V prime is still 2. And v is still 1. And we get -10. Any issues with that? Everybody good with that?
Yes.
All right, cool. So there are a few other rules that we're eventually going to learn, and sometimes they might give this type of problem using one of those other rules. So when we get to those other rules, we'll practice doing something like this a little bit more, but I think it's pretty easy. We got a couple other random little topics that we're going to talk about briefly, and then we're going to get into figuring out derivatives of trig functions. So we're going to start with reasons why a derivative might not exist at a specific point. And there are 4 of those. There are 4 reasons why a derivative might not exist at a point. And the first is a corner, the second is a cusp, the third is a vertical tangent line, and the last is if the function itself is discontinuous at that point. So we've got the first one, which is a corner. You probably can see what the corner is, right? Corner is just when we have a linear piece hitting another linear piece at a sharp corner. You see that graph right here? Yeah? We see that graph? We're good there? That's a corner. Derivative doesn't exist there. Why doesn't the derivative exist there?
Because like the slope suddenly changes at that point. So like the tangent lines at the approaching the point are both have different slopes.
Right, so from one side, right, that slope is -1. But from the other side, that slope is 1. And we have to remember, what is a derivative? A derivative is just a limit, right? And so if the limit from one side is not equal to the limit from the other side, well, then that limit can't exist. So this derivative can't exist. Does that make sense?
Yes.
All right. The second one is a cusp. And so a cusp is when we come into a point, but we come into that point from a curve. So this is a cusp right here. And same concept from the left-hand side. The slopes are negative, going towards negative infinity. Right? And from the right-hand side, those slopes are very close to positive infinity. And so those are not the same from either side. And therefore, that can't have a derivative exist there either. Everybody good with that one?
Mm-hmm.
All right, cool. Next one is a vertical tangent. Vertical tangent means that the slope of the tangent line is undefined, which would mean that the derivative is undefined. So anytime you have a vertical tangent line, the derivative can't exist. So like the graph right there. Any questions on that one? Okay, and then the last one is the discontinuity. So a discontinuity will tell us that the derivative can't exist, because if the function itself doesn't exist at that point, there's no way to have a tangent line at that point. Does that make sense?
Yes.
Cool. All right, anybody know what this first graph could be the graph of?
Absolute value.
Yep, looks like absolute value x. Anybody know what this one is?
Absolute value of a square root, maybe?
Yeah, that's going to be, it's going to be the square root of the absolute value of x, not the absolute value of the square root of x, but square root of the absolute value of x. Or this is also x to the 2/3 power. Those are a couple different graphs that could look like that. Hold on one second, and we'll talk about that. All right, and this last graph here, anybody know what that's the graph of? Anybody know what that one's the graph of? Cube root of x. Can you guys still hear me? I'm getting no responses, so.
Yeah, we can hear you.
Okay, just nobody knew what that graph was?
No.
All right, but now we know. All right, cube root of x. So those are just some examples. There's lots of graphs with vertical tangent lines, lots of different graphs with cusps. As we get into kind of the thick of this unit on derivatives, we'll see a lot of different cusps for other types of graphs also. Any questions or issues about any of that? All right. Next little thing we're going to talk about is motion and how these derivatives are related to motion problems. So you've probably in the past done a little bit of physics, or in your AIM-3 or honors pre-cal or something, you did a little bit of stuff with like looking at how particle might move in a plane or along a line, or something about how a like an object that's thrown might behave or something like that. That sound familiar?
Yes.
All right, cool. So we're gonna sort of expand on that a bit now. I think did somebody put something in the chat? It's not popping up again. Oh, there we go. Oh, it's just John telling me that he's sad about motion problems. Okay, that's fine. So if we are given a function that represents the position of a particle moving along a line, or a position of, anything moving in just a single linear direction, and we take its derivative, that should give us the instantaneous rate of change of that particle, which would be its velocity, right? That's how we measure the change in position of something, is with velocity. And so the rate of change of that position is the velocity, and the rate of change of a function is its derivative. So those should line up. The derivative of a position function should give you a velocity function. The derivative of a velocity function should tell you the rate of change of that velocity function, which would just be an acceleration function, because acceleration is how we measure a change in velocity. And then we also measure changes in acceleration with a function called the jerk function, and it's not a jerk like I would normally say, like the person sitting next to you in class that you hate, but there's nobody sitting next to you in class that you hate. They're just on the screen next to you or something. So not like that, but jerk just means a sudden change in acceleration. Okay. Just for fun, anybody know what the derivative of jerk is?
Snap.
Yeah, so there's two different names for it. One is jounce. It's also called snap. Right? Snap is the derivative of jerk. And what's the derivative of snap?
Crackle.
That's right. And what's the derivative of crackle?
Pop.
You should all know that one now. Snap, crackle, pop. Not sure why that's the deal, but that's the deal. Snap, crackle, pop. That's the derivatives of jerk. Snap, crackle, and pop. Anybody know the derivative of pop?
Goes back to velocity then after that.
No. Nobody? The derivative of pop? Come on, thanks to the, like, this was like it was like some stupid dance or song or something, like, I don't know, 5 years ago or 6 years ago, or I don't even know. Yeah, those are the Rice Krispies, but they're actually the derivative. They're also actually the names of the derivatives. So snap,
Wait,
crackle. Oh, yeah, what?
Oh, I'm having a crisis trying to decide whether this is real or not. Like, I really don't know.
Why would I lie to you?
It feels like a joke.
Oh, gosh, I'm a very serious person. I would never joke about anything. Yaya, to answer your question, what would I use snap, crackle, and pop for? Well, breakfast, obviously. I mean, what else would you use them for? I guess like a midnight snack, maybe? But in all seriousness to your question, yeah, we'll get back to what the derivative of pop is in a second because you're all disappointing me about that. It's not ever going to be used. We're never going to use anything past jerk, and we probably won't even ever use that. Like in a lot of physics situations, sometimes they'll use these higher derivatives. But you can think about jerk. So the way I think about jerk is if I'm going in my car and I'm driving and I'm accelerating at like a constant rate, and then I crest a hill. Well, even if I'm trying to accelerate at the same rate, as I crest that hill and start going down, I have a sudden change in how fast I'm accelerating because I've changed the trajectory of how I'm driving. And so that sudden change in acceleration would be the jerk. And suppose as I'm doing that, I hit a pothole, which causes my car to have a change in how that change in my acceleration is changing. So, well, that would be my snap. And suppose within that pothole, I run over a dead squirrel. Well, running over that dead squirrel is going to cause me to have a slight change in that snap, which will be a crackle. And as I'm running over that dead squirrel, suppose there was, I don't know, this is a big pothole. Suppose there was like and this pothole is clearly not in America. There's like a hyena in the pothole trying to eat that, and I crash into the hyena, and that's going to cause a change in my crackle, which will be my pop, and so on, you know, and so on, and so on, and so on, until there's no roadkill left. And yes, John, this story is based on experience. I have, yes, driven in my car at a constant acceleration while in a location that has both squirrels and hyenas, and then crested a hill with a pothole in it that had a squirrel that was already dead with a hyena that was eating it that I have crashed into and spun out my car and died. But then I came back to life because I am immortal. Okay, that was all good. Yeah, you're finally learning about the insanity of my life. On a separate note, Julianne, all serialness, that was good, but also sort of shameful at the same time. But it was also good. I give you credit for that. All right, let's see. Maybe I will make a movie from this experience, John. I could post it on my YouTube channel, and you can watch it there or something. It'll go along with many of the less math-related videos that are up there that were all taken during non-instructional time. If you've perused those, I wouldn't recommend it. But still, the problem is, oh geez, everybody's got requests in the chat. Another unboxing. I know there's all kinds of, the YouTube channel is shameful for me. I wouldn't look at it if I were you. But if enough people watch the videos, maybe YouTube will pay me and I will be rich. But I probably won't ever be rich because I'm a poor teacher. Yes, merchandise, that's a good idea too. I thought about that last year, but I haven't got around to it yet. Someday. I'll wear my batch math shirt next week sometime so you can all see it. But what we need is the derivative of pop. What's the derivative of pop?
Man.
Nobody? No, not corn, but that sounds right. Yeah, there we go. Somebody finally got it. It's lock. And then after lock should be what? It's like that stupid dance from a long time ago. Pop, lock, and don't you people know how to dance? Drop. Pop, lock, drop. And then the derivative of drop is shot. and then the derivative of shot is put. And these are all real. Even if you don't think that I'm telling you the truth, they are all real. And you will be tested rigorously on all of these. No, you won't be. But you should at least know them. Yeah? Good? Everybody good? Yeah? That was a fun little non sequitur about Rice Krispies and dancing and my YouTube channel or something. You don't need to know those. Just know that the derivative acceleration is jerk, and that's far enough. That's all you need to know. But it really is snap, crackle, pop, lock, and drop. So, and shot and put. Not lying to you. The last piece on here that is actually very important here is speed and velocity, and the relationship between speed and velocity. So speed is the absolute value of velocity, which tells us that speed is always positive or equal to 0. So it's always greater than or equal to 0, which means it has no direction to it. We talk about the speed of something moving to the right or the speed of something moving to the left. It's the same. Whereas with velocity, velocity has direction. So if I talk about a positive velocity, that's to the right, and a negative velocity is to the left. Or a positive velocity is going up, and a negative velocity is going down. Everybody good with that? Anybody got an issue? Can you guys still hear me?
Yeah, we can hear you.
Oh, good. Okay, I wasn't sure. My AirPods keep, like, one of them is dying and then the other one dies, and I take one out to, like, charge it, and then the other one dies while I'm talking. I don't know. It's been a fun morning. All right. Let's see if we can use these ideas about derivatives and some of the basic knowledge we have about displacement, that we hopefully have about displacement and velocity and averages and all that, to investigate how this particle that is moving along a line so that it's positioned at any time t greater than or equal to 0 is given by the position function s of t equal to t squared minus 4t plus 3, where s is measured in meters and t is measured in seconds. So we got a particle moving along a line. That just means that it's moving only in the x direction, right? It's moving to the right or it's moving to the left, one or the other, or perhaps both, as we go back and forth between them. So we may go back and forth between moving to the right and moving to the left. So the first question that's asked of us here is, what's the displacement of the particle in those first 2 seconds? So how do we figure out displacement? What does that mean? What is displacement?
How far it's moved from its original position?
It's how far it's moved from its original position. So we're interested in how far has this thing moved as it goes from t equals 0 to t equals 2. So in the first 2 seconds. So first we need to figure out the position at 0, and we need to figure out the position at 2. So what's the position at 0? Three. And what's the position at 2?
-1.
-1. Good. So what's the displacement? It's 3 minus -1, or 4 meters. And if we wanted to give some direction to this displacement, it displaced 4 meters in which direction? To the should be to the left, right? Because we're going from 3 to -1. Everybody good with that?
Yep.
All right, cool. What if we want to find the average velocity of the particle during the first 4 seconds? How are we going to do that?
Is this where you would use the derivative? Or like the velocity function?
Not yet, because we're looking at an average velocity. We're going to take the derivative to find the instantaneous velocity. So an average velocity is just a change in the position divided by the change in time. So our average velocity is change in position over change in time. So from 0 to 4, what's the change in position?
I don't think there is a change in position.
Yeah, there is no change in position because at s of 0, it's at 3, and s of 4, it's also at 3. So that's 0 over the change in time, which is 4. So 0. Our average velocity is 0 meters per second. Everybody good with that?
Yep.
Okay. So now to find the instantaneous velocity, we need to take the derivative. So for our instantaneous velocity, the derivative of s prime should be what? What's s prime?
2t minus 4.
Should be 2t minus 4. Yeah. Everybody good with that? I don't think I can. I think I lost my sound. I don't think I can hear you guys anymore. I think I might have fixed it. You guys can still hear me?
Yes.
I can hear you.
Yes.
I can hear you guys again. All right, perfect. Okay, so our derivative of derivative of s prime, which is v, should be 2t minus 4, which will be evaluated at t equals 4, which gives us what? Hopefully 4 meters per second. Okay, sorry, everybody. Hold on 1 second. I got to move to another room and figure this out. There's going to be a second. I got issues with my son's laptop and mine right now. So give me like 2 minutes. I'll be right back. Okay, sorry. Can you guys hear me all right?
Yes.
Yeah.
Okay, sorry about that. Yeah, I don't know, my laptop started dying, so I had to take it to the other room where I could plug it in. But then when I got to the other room, I discovered that my son wasn't doing what he was supposed to be doing. He's just running around the house, playing with whatever he feels like playing with, instead of like sitting there and listening to his teacher. And I can hear her on his Zoom call being like, "Hey, Max, do you have your whiteboard?" And he's just like not even anywhere close. So we had to have a short chat about what he should be doing right now. It's fun. Kids are great. All right, so everybody good with the velocity function being the derivative of the position function?
Yes.
All right, and we took the derivative and we got 2t minus 4, and we plugged in 4, and we got 4 meters per second. Yeah? Everybody good with that whole thing?
Yep.
All right. Let's find the acceleration of the particle. So the acceleration should be the derivative of the velocity function, and that's just 2. So if I take 2 and evaluate it at t equals 4, what do I get?
2 meters per second squared.
2 meters per second squared. Exactly. Good. And what if I had said, what's the acceleration at t equals 1? It would still be 2, right? And what if I said, what's the acceleration at 1,000? T equals 1,000. It'd still be 2, right? Because the variable fell out. It's just that constant. Everybody good with that part?
Yes.
All right, hold on 1 second again. All right, sorry again. We're having some issues here today. I apologize. Let's figure out when the particle changes direction. So how do we figure out when the particle changes direction? Suppose it's going to the right, and then it comes back to the left. Or suppose it's going to the left and then comes back to the right. What has to happen in between there? Between going to the right and then going back to the left, what has to happen?
It has to stand still.
It has to stop, right? It has to have a place where the velocity is equal to 0, right? Where it goes from the right, and then it goes back to the left, and then it goes back to the right. Each of those times where it changes direction, the velocity has to equal 0. So the only place where our velocity could equal 0, our velocity function was 2t minus 4, would be at t equals 2 seconds. Everybody agree with that?
Yep.
Okay, cool. So let's check and make sure that happens, because what we could have happen is we could have a particle that goes to the right and then slows down and stops, and velocity is 0, and then it continues moving from that same place again. Couldn't we have that situation too?
Yes.
Theoretically. So if we want to check and see if it actually changes directions at t equals 2, plug in a number less than 2, like 1, and plug it into your velocity function. If I plug in t equals 1, we get -2, right? Which tells us that if we got a negative here, it tells us that we're moving to the left. And then plug in something larger than 2, like 3, we get a positive, which tells us that we're moving to the right. So it changes direction at t equals 2 seconds. Is that good? Everybody good with that?
Could you also find the axis of symmetry for the displacement equation? Because like that's where the parabola starts like changing directions too.
Yep, you could, and that's I mean that's exactly what you did here. Finding this t equals 2 is where that axis of symmetry is. When we get into more of the applications, we're just doing like the little basic stuff right now with the applications, but when we get into the more complicated stuff, we're gonna see how those rules that you learned the last year, the year before, to find things like the axis of symmetry are derived from calculus. That you know, you learned it like you can find it by using x equals negative b over 2a, I think, right?
Yeah.
Yeah, so that we'll talk about it in a week or so, but that's derived using derivatives and using calculus is how they came up with that. All right, any questions on that motion problem? That took us way longer to get through than it should have, but that's my fault. So, all right, let's do one more quick one. Where we've got a stone that we're throwing vertically upwards on some unknown planet with a velocity of 10 meters per second. And it has a height, according to that equation, at any t value, 10t minus 1/2 t squared. And if we want to know what's the velocity after 2 seconds, how are we going to find the velocity?
Take the derivative.
Should be the derivative, right? Because this is just a position function. The height is just a position. So h prime should be v, which should be 10 minus t. And if we want to know what that is at t equals 2, I'll just evaluate it there and you get 8. The velocity is 8 meters per second. Good or no? All right. What if we want to know what the velocity of the stone is after it has risen 25 meters?
You can set 25 as to the displacement equation and then find t.
Exactly. So we can just say we want to know the velocity when the height is 25. So we need to figure out when the height is 25. So we'll plug in 25 for the height, solve this for t, which, you know, we can multiply everything by 2 to clear out that fraction. So 50 equals 20t minus t squared. And then we'll make this t squared minus 20t plus 50 equals 0. And unfortunately, that does not factor. So use the quadratic formula and tell me what the two t values are for this. So take a second to figure that out. You got a value there? Should have 2 values there.
I got 10 plus or minus 5 root 2.
10 plus or minus 5 root 2. People agree with that or no? I agree with that. So there's two of them. There's 10 plus 5 root 2 and 10 minus 5 root 2. Which one do we want to choose? Which one is the one where it's risen 25 meters? Particle goes up and then it goes back down, right? So the first time it hits 25 meters would be when it's risen 25 meters, and which time is that going to be, the plus or the minus?
Minus.
Should be the minus, right? 10 minus 5 root 2, all of that, or 10 plus 5 root 2. So let's say that's our t value. T equals 10 minus 5 root 2. And we want to evaluate the velocity at that point. So the velocity is 10 minus that t value, 10 minus 5 root 2. And what does that simplify to? Just 5 root 2 meters per second. Any issues with that? Everybody good with that?
How'd you know that it was minus and not plus?
10 minus 5 root 2 is just a smaller number than 10 plus 5 root 2. Right, and so it's going to be at 25 meters twice, once on the way up and once on the way down. And so we chose the one where it's on the way up because it says after it has risen 25 meters. So that'll be the first t value. Does that make sense?
Yeah.
Okay, cool. Any other questions on that? We're going to do a lot more with motion problems as we move throughout the year. We'll do a little bit more in another week or so, and then right before you guys are done with the first 9 weeks, or right when we come back for the second 9 weeks, we're going to do quite a bit more. So we'll spend a lot of time with motion problems soon. So we're going to change gears a little bit, and we're going to start talking about trig functions and how to take the derivatives of trig functions, because right now we're really only just dealing in polynomials or rational functions with our product and quotient rule and our power rule. Doesn't give us a lot of flexibility on the functions we can look at, and we want to basically be able to look at any function we're interested in. So how do we find the derivative of sine x? Any thoughts on how to find the derivative of sine x?
Look at its graph and approximate.
There's one idea. We could look at its graph and approximate, but that's not going to give us an exact value. We want an exact value. Well, if we don't know what the derivative is or how to find the derivative, what do we usually do?
Do the limits thing.
Do the limits thing. So the limits thing will be the limit as h approaches 0 of what? Sine of x plus h minus sine of x all over h. So we have the limit as h approaches 0 of sine x plus h minus sine of x all over h. And any thoughts on what we can do with that? Anybody remember an identity with sine of a plus b?
Wait, could we just divide it up into parts and make it into like the sine of x? Oh wait, oh no, there's an h on the bottom. Okay, never mind.
Okay. So we have to separate out sine of x plus h somehow. That's going to be our next step. So do we remember the identity for that? Anybody remember the identity for that? I didn't ask you to memorize this one, but it's on the long sheet that you should be familiar with.
Is it sine of x cosine h plus
It's sine x cosine h, yep.
plus cosine x sine h.
Yep, that's exactly right. And then we still have a minus sine x all over h. So what can we do with this now? Should we plug in h equals 0? If we plug in h equals 0, what do we get? Still 0 over 0, I think. So what do we have in common here? Both the first and the last terms in the numerator both have a sine x in them, right? So let's separate those two terms by themselves. So the limit as h approaches 0 sine x cosine h minus sine x all over h, plus the limit as h approaches 0 of cosine x sine h over h. Everybody good so far with that?
Shouldn't it be -1 on sine x cosine h?
Oh, well, I didn't factor out the sine x yet, so we'll do that
Okay.
now. Yeah, so now we'll factor out the sine x. Yep. And then this one, I might want to separate this one into two different ones, right? How about the limit as h approaches 0 of just cosine x, and the limit as h approaches 0 of sine of h over h. And why might we want to do that one? Because we know what sine h over h is, right? What about over here? Do we know part of this one? Don't we know that one? What's the limit as h approaches 0 of cosine h minus 1 over h? We should know this one. Should be
0.
0. So over here we've got cosine x for h approaches 0 of cosine x, and this is just a 1. And this will give us sine x times 0 plus cosine, and sine x times 0 is just 0. So we end up getting the derivative of sine to just be cosine. Everybody okay with that process? Any issues with that? All right, so we're going to want to know that the derivative of sine is cosine. What about the derivative of cosine? Any thoughts on what that should be?
Negative sign.
Okay, why?
I don't know. I just searched it up.
You just know it, right? Yeah, okay. So we're going to do we could go through, and in fact, we're not going to bother to go through the whole same process, but we're going to use a limit as h approaches 0 of cosine of x plus h minus cosine of x all over h. And eventually, as you go through there, you end up getting f prime of x equals negative sine of x. So I'm not going to make us go through and prove it. It's done almost exactly the same way as the one we just did with sine. So if that one made sense, you could do the cosine one also. Okay? So the derivative of cosine is negative sine. Now, let's see if we can use those two derivatives and not have to do any more limits and find the derivative of the other four trig functions that we're going to concern ourselves with this year. So first off, tangent x. How could I rewrite tangent x to find its derivative?
Sine x over cosine x.
Right, and why does that help us? Because what? We know the derivatives of sine and cosine, right? And we can use which rule?
Quotient rule.
Quotient rule. So it'll be denominator cosine x times the derivative of the numerator. So the derivative of sine is another cosine x minus the numerator times the derivative of the denominator, which is negative sine x, all over the denominator squared, which will give us a cosine squared in the numerator. And then the two minuses give us a plus. So plus sine squared in the numerator, all over cosine squared x. And cosine squared x plus sine squared x is
1.
1. So we have 1 over cosine squared x, and we'll normally write this as secant squared x. So the derivative of tangent is secant squared. Everybody good there? You'll want to memorize that one. Let's do secant x. How should we rewrite this one to use one of our rules that we know?
One over cosine.
1 over cosine. Good. Okay, so 1 over cosine x. And we can just use the reciprocal rule on this one, right? So the derivative should be negative derivative of the denominator, so negative sine, divided by that denominator squared. Negatives cancel, and we've got sine x over cosine squared x. And normally, we rewrite this as sine x over cosine x times 1 over cosine x, which is 1 over cosine is secant x, and sine over cosine is tangent x. So the normal notation for the derivative of secant x is secant x tangent x. Good or no?
Yeah.
All right, let's take a look at cosecant x. We could rewrite that as 1 over sine x. And then the derivative will again be done with the reciprocal rule, which will be negative derivative of sine. So negative cosine x over sine squared x. And then we will rewrite this as negative 1 over sine x times cosine x over sine x. And then that is negative cosecant x cotangent x. And that's our derivative of cosecant x. Everybody good with cosecant x? All right, last one, cotangent x. Two different ways we could rewrite this one. What are the two different ways we could rewrite this one?
1 over tangent x or cosine x over sine x.
Yep. Any preference? We'll do whichever way you want.
One over tangent.
All right, 1 over tangent x. 1 over tangent x. So our derivative should be negative derivative of tangent over tangent squared. And that's not super simplified. Sorry, tangent, yeah, tangent squared. So we'll rewrite this a little bit here as negative 1 over cosine squared for secant squared. And then tangent squared in the denominator is the same as a cotangent squared in the numerator, which would be a cosine squared over a sine squared. The cosine squareds will cancel. And we have negative 1 over sine squared or negative cosecant squared. Any questions on that one? All right, here are the 6 of them all in one page. You need to memorize all 6 of these. I'm going to expect that when I see you guys on Monday, you know them all by heart. So should be pretty straightforward. Sine to cosine, cosine to negative sine. Tangent to secant squared and cotangent to negative cosecant squared. So those are pretty similar. And then secant to secant tangent and cosecant to negative cosecant cotangent. So those are pretty similar too. And you'll probably notice that all of the co-functions have a negative in their derivative. So cosine, cosecant, and cotangent, the derivatives all have a negative piece to them. Everybody good there? All right, let's do a couple real quick before I let you guys go. Let's find the derivative of tangent x over x. So what rule will we use?
Quotient rule?
Quotient rule. So f prime of x should be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, which is just 1, all over x squared. And that's your answer. Pretty straightforward as long as you know the trig derivatives and the quotient rule. Any issues with that one? All right, here we've got secant x over sine x. Let's try this one. Again, quotient rule. So f prime of x should be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Good with that so far? Okay, and this is a lot of trig functions in there that we could simplify a bit. Secant is 1 over cosine, so sine times 1 over cosine is what?
Tangent.
Tangent, and tangent times tangent, that would be tangent squared x, and then secant times cosine should be what?
1.
Right, because secant is 1 over cosine, so we got cosine over cosine, and then all over sine squared x. This is a good answer, no more simplification needed. Just keep in mind that if you were taking a multiple choice test, like the AP test has a bunch of multiple choice questions, the answer might not look exactly like this. They might have left it like this, or they might have simplified it part way, or done some simplification but left some of it, or they might have gone and done more rearranging with this, like did tangent squared divided by sine squared minus 1 divided by sine squared. So just be able to rearrange your trig functions to replicate any multiple choice answer that they might put on for a problem like this. Does that make sense?
Yes.
All right. Let's do this one and then maybe one more and then we'll be done. So finding the derivative of secant squared x. How are we going to do that?
Product rule?
Yep, that's exactly right. We'll just turn this into secant x times secant x and use the product rule. So f prime of x should be first function times the derivative of the second function, and then plus the second function times the derivative of the first function. So we've got secant squared times tangent plus secant squared times tangent, which is 2 secant squared x tangent x. Good or no? All right, this is the last one we're going to do today. Let's find the fourth derivative. So we'll do the first four derivatives of sine of x. So what's the derivative of sine?
Cosine x.
Cosine x.
Okay. And what's the derivative of that?
Negative sine x.
Okay. And what's the derivative of that? Remember that that -1 in front is just a constant.
Negative cosine x.
Yep, negative cosine x. It's just a constant times the derivative of sine. And what about the fourth derivative then? That constant of the negative stays, so it's a negative derivative of cosine, which is what?
Positive sign.
Yeah, once you put the two negatives together, it becomes positive sine x. And so we'll see that, you know, sine's a cyclical function, as we know, but even the derivatives cycle back through. So the fourth derivative of sine goes back to sine. The eighth derivative will also be sine, and the 12th derivative, and the 16th derivative, and so on. All right, I think that's enough for today on a Friday. We'll be done 5 minutes early, I think, or else maybe we're running late. I don't really know. Any questions on anything we did today?